Hello everyone. This is the third lecture in a series of 5 lectures for the first part of the course, Cognitive Modeling. In this course, we have been so far talking about how, in order to investigate a theoretical account of a cognitive process, we can build a model, a computational model, to simulate the process by receiving the same kind of input or information and generating the same kind of output or behavior as humans engaged in the cognitive process that we want to investigate. So far, when talking about computational models, we have only talked about them as a black box, with the exception of a couple of very simplified examples. We really haven't talked about the internal structure of these models, what they look like, what the knowledge is represented there. And this is a topic of conversation in this and the next 2 lectures. What we want to do is to discuss common modeling frameworks in a historical way. So we want to start with the very first generations of computational models and then talk about how the internal structure, the representational formalisms, and the learning mechanisms have changed over time. The first generation of models that we will actually discuss in this lecture are called symbolic models. These are models implemented in a symbolic setup, very heavily influenced by the first generation of artificial intelligence systems. So what happens here is that typically a symbolic system is used for representing knowledge, and then logic-based rules are used to make inference based on the represented knowledge. These models were very popular, but gradually went out of fashion, and a new wave of models took their place. This new wave was usually called connectionist or artificial neural network models. These were models that were originally inspired by the architecture of human brain, although very loosely. And the main idea behind them was that instead of representing knowledge in the form of a set of symbols, knowledge was represented in a more distributed fashion and also was potentially processed in parallel, similar to what has been observed in human brain. These models were very popular, but they gradually also became unpopular due to some computational complexities and inefficiency. Although in recent years they're coming back into fashion, they're becoming more and more popular, and we will talk about them in the next video lecture. The last wave of models that I very loosely and generally refer to as probabilistic models became trendy following the success of statistical machine learning techniques. The idea here was to combine the descriptive power of symbolic models of human cognition with the flexibility that's provided in the connectionist models, so to get the best of the 2 worlds. And this would be the topic of conversation of the last lecture in this section of the course. So let's start with symbolic models. The idea here is to use a very explicit formalism for representing and processing knowledge through using a set of symbols. So knowledge, as I said, is represented as a set of symbols and their propositional relation. To give you an example, let's say we are interested in the meanings of words, and what we want to do is we want to represent concepts such as apple or cat, or even abstract ones such as love or justice, as symbols. In this case, I'm using apple, the written form, as a symbol, or cat, the written form, as a symbol. If you want to implement and store this kind of information in a computer, then we, instead of having, the red, juicy, round fruit, we have to use yet another symbol called O1, for example, as in object 1. If object 1 is an apple and object 2 is a cat, then we have to explicitly specify what we mean by that, what kind of characteristics these objects have. This can be done, for example, by specifying a set of relations or specifying a set of attributes for each object. For example, the color of object 1 is red. The animate status of object 1 is false, which means that object 1 is not animate. It's not an animal or a human, and it has to be a physical object. The category of object 1 is food. And similarly, we have appropriate attributes for object 2. So this is how what our model knows about the world is represented in a very explicit way. So let's go back to our simple example of the categorization model. The idea was to feed the model with a set of examples or items and then have it form certain categories. If you want to do that in a symbolic fashion, we basically need to implement a learning mechanism or processing mechanism for going over the attributes of these objects and generating some categories. How do we do that in a symbolic model? Basically, in symbolic models, processing and maintaining our knowledge about the world is done through a set of general rules or schemas, which are sometimes under certain constraints. Again, to give you an example, a rule can look like this. If an object is not animate, this is what the first line says. If animate of O1 is false, means if the object O1 is not animate. And if it's edible, which is represented as edible of O1 is true, then object O1 must belong to the category food. So that's what the last line says. Category of O1 must be assigned to food. So this is a very simplistic way of saying put all the non-animate edible things into the category food. Some of the rules can be a bit more meta level. For example, this rule, take a look at it and try to see if you can understand what this rule implies. It basically says if the animacy of object 1 and object 2 is the same, so they're both animates or both inanimate, and they have the same shape, meaning they have the same value for the attribute shape, and if they perform the same function, then they must belong to the same category. You see that here the model is actually incorporating a very clear basic assumption at the computational level. It is saying that in order to form categories, the features that we pay most attention to as humans are shape, function, and animacy. Whether it's correct or not is not the topic of our lecture right now. What I'm saying is the basic assumptions and principles that model is built on are incorporated into these general rules. Now, when you form a logical rule, this rule, the way the model understands it, has to always be true. So if you have a rule like this, if an object belongs to the category bird, then it must be able to fly. This rule in most cases is true, but we all know that there are exceptions to this rule. There are birds such as penguins and ostriches which cannot fly even though they belong to the category bird. So the solution that the symbolic modeling framework provides is, okay, you can define a rule, but you can also list a number of exceptions to that rule. So in this case, you see that we have a separate line under the rule which iterates the exceptions to this rule, things that belong to the category bird but cannot fly. This seems like a straightforward solution, but it really is not always very easy. There's a classic example for this phenomenon, and that's the definition of the word bachelor in English. Bachelor in English means a man who is not married. And if you think about it, it is not very difficult to define a rule that defines what object belongs to the category bachelor. So it will look something like this. If the gender of a symbol or an object is male, and if this object is not married, then you can put it in the category bachelor, or you can decide that the value of the attribute bachelor is true. Basically, it's a translation of that sentence you saw before, bachelors are males who are not married, in a logical form. Now, although it seems more or less accurate and matches our intuition about the meaning of the word bachelor, there are cases where it's really difficult to decide whether this rule should apply or not. For example, is Pope a bachelor, in your opinion? Seems like Pope will satisfy the constraints of this rule because he's male and he's not married. But at the same time, really, Pope doesn't typically strike us as a classic example of a bachelor. So you see that this framework has its own limitations because of its rigidity, because once you have a rule, you have to either have a set of very clear exceptions or you have to apply it to all the cases. I want to give you an example in another domain, in the domain of language. In the domain of language, a symbolic framework has been used very extensively. This is called a context-free grammar, or a CFG. This is a formalism that's symbolic in nature, and it's developed to represent the grammatical knowledge of language. So rules such as this: in order to form the past tense form of a verb in English, you have to add ed to the root form of the verb, are displayed and represented in a logical form the way I'm showing to you here on the slide. Again, as we know, there are several exceptions to these general rules, and you can list those under the rule. For example, the verb put doesn't follow this general rule. The verb go doesn't follow this general rule. Now, these are, again, limited examples. I want to give you a real-life example. That's one of the very first models of how translation takes place. So the translation process you're all familiar with. You hear a sentence in one language. If you speak that language, you basically form some representation of this sentence, and then you can regenerate it in a different language. Here we have a translation of a sentence from Dutch to English, for example. So how does this happen typically? It has been suggested that the translation process looks something like this. You receive an utterance in a source language, you basically reform this utterance based on what it means. So you represent the meaning of this utterance, and then you regenerate a new sentence in the target language which explains the same meaning. So on the one hand, you have the comprehension process where you understand a sentence in the source form, and then on the other hand, you reproduce the meaning in the target language. Now, can we model this process in a symbolic model? This is something that in 1954, a group of researchers in Georgetown, IBM, tried to experiment with. What they did was they tried to build a symbolic model of translating Russian to English using a dictionary and a set of rules. This was a very limited model. There were only 250 words in the Russian language. There were only 50 sentences that the model could translate, and there were only 6 grammar rules in the model. And you see real pictures of the secretary entering the data, the engineer actually setting up these rules in the machine, and then the visitors who are looking at the translation of the input in Russian sentences being printed on a printer. What I want you to see is how the behind the scenes look like. So the first box here is showing you the dictionary. There are Russian words on the left-hand column, and then there are English equivalents of these Russian words, and then there are some mysterious codes that are added there in order for the machine to be able to work. And if you look at the rules are not very easily understandable. They look like this. If first code is 110, is third code associated with preceding complete word equal to 21? If so, reverse order of appearance of words in output. So this is a bit difficult for a layman to understand exactly what this rule is representing, but they had to very carefully engineer these rules in order for the machine to generate the correct translation for those 50 sentences. And if you look at the dictionary lookup procedure, it looks something like this. Of course, I don't expect you to understand it. I just want to show you how complicated the process was to build a symbolic model that works even for a very small subset of the language. So this is the kind of publicity that this model received at the time in 1954. This is what New York Times published about it. Dr. Hertz said that the corporation would now design a machine particularly fit for translating rather than for general computing utility. Such a device should be ready within 3 to 5 years, when the Georgetown scholars believe they can complete the literary end of the system. As soon as cards for Russians are complete, sets will be made for German and French. Then other Slavic, Germanic, and Romance languages can be set up at will. Now we are in 2017, and you might think, these people were very optimistic about how easy this task is. So, symbolic models, they had certain advantages, the most important of which was that the formalism and the representation of knowledge is explicit. We know exactly what kind of knowledge they represent. And the learning and inference mechanisms are computationally very well understood because they're based on formal logic, which has been studied and entrenched for centuries now. The disadvantages are that the traditional symbolic models do not really rely on statistical characteristics of the input data, which has been shown over and over again that is very important to human beings. They cannot also easily deal with noise and ambiguity in the data, which is also a very serious limitation of a cognitive model. So in the next lecture, we will move on to the next generation of the models, the connectionist models, and compare them with these symbolic models with